Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we are going to discuss approximating solutions to first-order initial value problems. So in this topic we will focus on first-order initial value problems. We will observe how solving such problems is equivalent to performing integration. We will list the methods that we will use to approximate solutions, and we will observe that these solutions parallel algorithms we've already seen, specifically algorithms we've seen for approximating integrals. We will then show the meaning of ordinary differential equations together with their initial conditions visually so that you can get a picture as to what's actually going on. Now to begin, we're going to be solving, or at least approximating, solutions to first-order initial value problems. And a first-order initial value problem is any differential equation that can be written as follows. The derivative is a function of the independent variable and the value of that function. And an initial condition is specified. Now, in calculus, you're going to realize that the techniques used for solving higher order initial value problems, boundary value problems, and partial differential equations often differ. So you're learning many different techniques to find exact solutions for different problems. However, the numerical techniques we will be using to approximate solutions can, however, be generalized. What that means is what we will be covering here will actually also allow us to solve, for example, systems of first-order initial value problems, higher order initial value problems, and systems of higher order initial value problems. But not only that, we will continue to use these techniques when we are calculating or solving boundary value problems and partial differential equations such as the wave equation and the heat equation. Now we could immediately jump to explaining the Dormant Prince method for approximating such a solution. After all, this is a reasonably new algorithm specified in 1980. This is an algorithm that is likely defined within the lifetime of your parents. Certainly within my lifetime, I was watching Linda Carter in Wonder Woman and the A-Team at that time. Unfortunately, if we just immediately jump to the most appropriate algorithm, you would not understand the issues at hand. You just memorize this algorithm and the purpose or the benefits would be lost. Consequently, just like you started with Riemann sums for approximating an integral, we are going to build up solutions or approximations to solutions of initial value problems with simpler algorithms until we can correctly understand the purpose of the Dormant Prince method. It's also useful to remember that when we are solving a differential equation, specifically an initial value problem, this is essentially integration. After all, if we have this differential equation, and if we were to integrate this from t0 to t on both sides, well, from the fundamental theorem of calculus, we can substitute the left-hand side with simply the expression we see there, and therefore we have that the difference between these two values is equal to that integral. Bringing over the one term to the other side, we see that essentially the solution y of t depends on an initial condition plus an integral. The problem is the integral has a function that may actually depend on the function we're trying to solve. So it's not that easy. However, we will use this in the future. So since solving an initial value problem is essentially an integration, we're going to see that the techniques actually are sort of similar. So the algorithms we're going to see proceed as follows. We're going to start by looking at Euler's method. However, Euler's method is actually very similar to the Riemann sums you saw in your first calculus course. Hoyne's method we're going to see is actually similar or parallel to the trapezoidal rule. Fourth order Runge-Kutta is actually an analog of Simpson's rule. And then we will start moving on to adaptive techniques. We're going to look at adaptive Euler-Hoyne, and there's no real equivalent in integration algorithms. Adaptive Dormant-Prince, again, no equivalent, but we'll also look at something called the backward Euler method. Again, no real equivalent version. However, we're going to start with looking at algorithms that are similar or analogous to algorithms we've already seen in approximating solutions to definite integrals. Now, to understand how these techniques work, it's also often useful to understand what the ordinary differential equation means visually. Now, with the implicit function theorem, I've argued that we can write most first-order ordinary differential equations in the form of the derivative being a function of t and y of t. What that says is that given a solution y of t, then the slope of that solution must equal the function on the right-hand side. So, for example, here is one such ordinary differential equation. The derivative is negative 0.2 times y minus sine of t minus 0.1. And the right-hand side is our function of both t and y. What we can do now is we can plot arrows at different values of both t and y, plug those values into the right-hand side of that differential equation, and you will see that that gives us a slope. Well, in this image here, we see the slope at different points. Basically, if a solution passes through a point, it must pass through that point with that slope. All right, so for example, if the initial condition is y at 0 equals 1, there's actually only one function that satisfies both the condition, shown there, where you can see when t is equal to 0, the value of the function is y equals 1. The slope there is negative, and as it proceeds, you can see that the function does seem to follow the slopes as indicated in that plot. Alternatively, if you were to specify the initial condition y at 0 is equal to 0, then once again there's a different function, and again only one unique function that satisfies both that initial condition and the differential equation. So that is a function where absolutely everywhere, if you simply take the value of the function and the value of t, plug it in, it will have a slope equal to the right-hand side. Indeed, any initial condition you specify is actually going to result in a different solution, and you will notice that these solutions never actually cross. So our goal is going to be to approximate these solutions numerically. Fortunately, to approximate these solutions, we will actually use the differential equation we're given. So suppose we have the initial condition y at 0 is equal to 1 as shown here. Well, if we substitute t equals 0 and y at t equaling 1 into that differential equation, we get that the slope at 0 is negative 0.3. So approximately that in the image. Well, you also know from Taylor's series that y at 0 plus h is equal to y at 0, the initial condition, plus h times the slope, which we just calculated. So given an h of 0.5, we get that approximation there. So following this topic, you now have a better understanding of what an initial value problem is. You are aware of how approximating such solutions are equivalent to performing or approximating integrations. And you understand how the differential equation gives us the slope of the solution at various points. And at the same time, you understand now how the initial condition specifies one specific solution to that ordinary differential equation. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!